So let me go back to this video.
We're going to use a kitchen sink faucet.
So in the video, he talks about two types of flow, laminar and turbulent. And you can clearly see the effect here. In the first case, when the flow is laminar, you can see that the flow is really uniform. You know, it's the flow particles are moving in parallel. But when the flow becomes turbulent, it's not the case anymore. So you see that the flow fluctuates and it's not uniform anymore. In first case, the streamlines are all parallel, but in the second case you have so in the first case you have flow flowing really nicely, but in the second case you have things like this happening, right? So this is totally random and chaotic. And the same thing can happen in airflow as well, just because it's easier to visualize in water. That's what I showed you here. And if you notice that in this test, it's the same flow. I mean, it's the same fluid, right? But you can clearly see that in one condition you have laminar flow, in another condition you have turbulent flow. And we need to know when we will have laminar flow, when we will have turbulent flow, or we need to somehow quantify this effect. Okay, so in our equations we need to include the effect of flow type in our calculations. Okay, so to start with, let me talk about viscosity. So that's one thing that is effective in determining the flow type. So let me just read through the definition of viscosity here. Viscosity describes a fluid's internal resistance to flow and may be thought of as a measure of fluid friction. So I think it's a very nice description of it. You can just think of it as fluid friction. When you have a streamline of flow flowing on top of another streamline, there's the friction force between them. So far, we only talked about pressure forces, and we said the aerodynamic forces are created by pressure forces. And by definition, pressure forces are always perpendicular to the surface, right? These green arrows, they are always perpendicular to the surface. And now, due to this flow friction, in fact, there are some tangential components as well. So these are red arrows here, and these are the forces that are there due to the viscosity of air, viscosity of the flow. Okay, so what determines when you have a laminar flow or when you have a turbulent flow is the significance of these forces. In certain cases, you have these perpendicular forces, or the green forces, are much more significant. Or in the other extreme case, you have the other way around. You have the tangential forces more significant, and what determines the flow type is the ratio of these two forces. Okay, so let me show you another animation to show you the difference between turbulent versus laminar flow. So as you can tell, the one on the left, this green one, is a laminar flow. So the flow is much more smooth in this case, whereas in the other case it's rough. It's very the turbulent case for this airflow. But let me show you another animation. I think this is even nicer. I wonder if I can make this bigger. In this case, there is no direct flow, but what we have is we have two cups of fluid, and an object is dropped into the fluid, and the response you get is quite different, right? So in the below case, the blue one, when the object hits the surface, it slowly sinks into it, right? You don't see any like random chaotic splashes around. Whereas if you look at the top one, that's exactly what you get. When the object is dropped into the fluid, you get these random splashes. So the flow or the fluid moves in a chaotic manner, right? So this is a turbulent case and this is a laminar case. Okay, so let me ask you a question here. What do you think is the difference between these two cases? So viscosity, so that means these fluids are different, right? Is that what you're saying? So the blue fluid has a different property than this other fluid. Is that? Okay, so let me ask you this. Can you have, so is there a possibility that these two fluids are the same? So you have the same fluid, but in one case you get this response, but in the other case you get this one. You think that's a possibility? Yes? So you're saying that both of these can be water? Does everybody say yes to this, or? Okay, so if I tell you that one of these cups is full of water and the other is full of honey, so which one do you think would be the honey? Blue one, right? Because honey is a much more sticky substance compared to water. So you would naturally expect honey to look like this. But anyway, so let me go back to my previous question. In fact, it is possible that you get these two different responses from the same fluid. Obviously, the viscosity is an effect here. So let me go back to the definition of viscosity. And maybe thought of as fluid friction. So if you have a viscous fluid, then that causes the difference you get in these two animations here. But as you see in the other video, even for the same fluids, you may have sometimes a laminar behavior and sometimes a turbulent behavior. So obviously viscosity is not the only factor. There is something else. Because if what determines the type of flow you get was only determined by the viscosity of the fluid, then in this video you would always get the same type of behavior. But obviously that's not the case. Sometimes you see a laminar flow, and sometimes you see turbulent flow. And what I'm saying is you can get the same thing in such a test as well. You can find such conditions that so in fact it may be the other way around. I can give you conditions where you have this cup full of honey and you drop an object and the honey, that such thick substance would splash violently and chaotically, just like this case. Or I can give you conditions such that an object dropped into a cup of water would sink just slowly, just like in this example. So obviously viscosity is an important factor, but there are other things. And these other things are all taken into account using this Reynolds number. So let me... So there are various factors that determine when the friction forces become significant or negligible. Reynolds number is a non-dimensional number that practically tells this. A very important factor is how sticky the fluid is, measured by its viscosity. From our point of view, this is not an issue since we almost always consider aircraft flying in air. So in our case, our fluid is always air. It's not like sometimes we fly through water or sometimes we fly through honey. We always fly through air. So the viscosity property of our fluid doesn't really change significantly. So it may change due to temperature, but the change there will be negligible. So other factors are the speed of the flow and the size of the object. So these are important as well. In fact, this is what you get here. In the laminar case, in the first part of the video, the speed of the flow is low, and you have laminar flow. And when he turns on the faucet more, it starts getting turbulent, and that's because the flow speed increases.
However, if I turn the water flow rate up, the flow stream becomes turbulent. You notice if I put my finger behind the water stream now, you see the image fluctuate.
Okay, so let's take a look at this Reynolds number. Reynolds number is a dimensional number that gives a measure of the ratio of inertial forces to viscous forces, and consequently quantifies the relative importance of these two types of forces for given flow conditions. So here it says the ratio of inertial forces to viscous forces, but you can also view this as the ratio of these two types of forces here. The pressure forces, which are perpendicular to the surface, to the tangential forces caused by the fluid friction. So the Reynolds number is just the ratio of these two forces. Okay, it's a non-dimensional number again. So a force divided by another force, you get a non-dimensional number. Okay, and if you put this into equations, this is what you get for the Reynolds number. The Reynolds number is defined by this relation here, and on the numerator you have the air density, or the density of the fluid, the speed of the fluid, the speed of the flow, and some distance characterizing the flow. If you're talking about an aircraft, the mean aerodynamic chord length is used. Or if you are talking about a flow through a pipe, just like in the video, now for that case you use like the diameter of the pipe. And then on the denominator you have mu, which is the coefficient of dynamic viscosity. And this is a property of the fluid. So if you put all these quantities into this relation, you get the Reynolds number. So let's take a look at these sample Reynolds numbers. For full-scale airliners, you have the Reynolds number is really large. It's on the order of 10 millions. So that means the distinction of the flow is completely negligible, right? So that means the pressure forces are 10 million times larger than the tangential friction forces. But if the scale of the aircraft gets smaller, then the Reynolds number is reduced. For example, if you consider a typical model aircraft, model airplane, it is on the order of 200,000. For even smaller mini radio-controlled aircraft, it is even less, on the order of 30,000. And this Reynolds number is defined for any flow. It is not just for aircraft. So even the flight of a bird or an insect has a corresponding Reynolds number. And if you look at that, they are even lower. So for a small bird, the Reynolds number can be on the order of 100. Or for a fly, it's even smaller, it's on the order of 1. And for microorganisms moving in water, it may be on the order of 0.0001. So that means if you have a little organism swimming in water, the Reynolds number can be on this order. So that means for that organism, the friction forces are much more significant than the other forces. Okay, so here's I'm just explaining what I just told you. So these are the two forces you are looking at the ratio of. So for large aircraft, this is usually the case. The stiction forces or the friction forces are much smaller. But for other organisms, like for flies and for other biological things, you may have this case where the friction forces are more important. So in other words, what determines the flow characteristic is the Reynolds number. So everything is taken into account in this simple number. So when you go to this experiment, for example, the difference between the laminar and turbulent flow is that you have the speed of the flow changing. So this is what determines the change between those two cases. Okay. So I have this video. It's a rather long video. I don't really want to show all of that, but I can post this on on the lecture notes, so you can watch this later on. So here there are basically 4 experiments. In the first case, you have the Reynolds number that is very low. So this is a complete laminar flow. So the fluid here, it just piles up. It doesn't even sink into this other fluid. It just sits on top of here. In the second case, the Reynolds number is 10. And you see that it penetrates into fluid a little bit. And in this case, it's 200. It penetrates even more. But still, the flow is quite uniform. It's quite laminar. And in this last case, you finally get a turbulent flow. So you can clearly see that the effect of turbulence here. So typically for low Reynolds number flows, you get the flow is laminar. And as the Reynolds number is increased, the flow becomes turbulent at one point. So for our experiments, for aircraft, the Reynolds number is quite large, so we never really see the Reynolds numbers on this order. So if you go back to the other table, especially in this course, we'll be only considering very large Reynolds number aircraft. So these are the Reynolds numbers for the type of aircraft we'll be studying in this course. So it's always a very large Reynolds number, but still the difference between this and this can be quite significant. So when you are making wind tunnel tests, you need to check the Reynolds number as well. And you should make sure that the Reynolds number should be comparable. So if you have a very, very small model aircraft, then the Reynolds number can be much smaller than the real flight. In that case, you cannot really use the coefficients directly. So this is an example. So these are the lift coefficient values obtained at different angles of attack. So the horizontal axis is the angle of attack axis. So what you see here is the lift coefficients are measured. Well, you measure the lift force, and from there you obtain the lift coefficient for different angles of attack. And as you see, at different Reynolds numbers, you get different values. So for example, at 10 degrees, if the Reynolds number is 20,000, your lift coefficient value is this much. It's on the order of 0.5. But for the same angle, if the Reynolds number is 3 millions, then the lift coefficient is much larger. See? It's almost 3 times greater. So, so you have to make sure that when you do wind tunnel testing, the Reynolds number should be comparable to the Reynolds number of your actual aircraft. Otherwise, you cannot use the coefficients. And as you see in this graph, the difference can be as large as 3 times. So obviously your coefficients will give you wrong estimations. Okay? So by the way, this turbulence is really very difficult phenomena. Nobody understands it completely because it's random. You cannot possibly calculate it, right? And so let's go back to this animation. You can't really have a computer's prediction of such a chaotic flow because it's totally random. But laminar flow is not the case. Laminar flow is quite predictable, and in fact, the laminar flow is so uniform and so smooth that it is reversible. So when I said at the beginning, today's lecture would be very interesting, I was referring to these videos I'm going to show now. So let me show you this experiment.
It's never been done on TV, and it's something you have to see to believe. So Sean is across the studio.
Okay, so here they're going to demonstrate a laminar flow, and I'm sure you will all be surprised to see that.
It's never been done on TV, and it's something you have to see to believe. So Sean is across the studio with a big bang turning chaos into order.
Let me show you the apparatus because people at home are going to look at it and go, wait, did I just see that? So let me show you what it is. I've got a large cylinder here, and inside the large cylinder is a small cylinder. And it kind of looks like this. I've got a beaker as a demonstration. So a large beaker and a small one inside the large one. That's kind of what we have. And that little wall that you see that's right here is filled with corn syrup. Right? So we've got corn syrup that's kind of poured inside. So that's where we are. Why corn syrup? It's just because it's very viscous. All right? So it's very viscous. And now I colored some corn syrup here. I'm going to shoot the colors in here. So let me put it down inside here and see if I can just kind of shoot the color down inside. So there's our blue dot. Okay. See our blue one right there. And now you can imagine we've got corn syrup everywhere. So there's blue, and here's a red dot. So that's kind of cool. The red one right here in the middle. Nice. There's a nice little red shot right there. Good. Patriotic. Thank you very much. I'm glad you noticed. All right. You can see what happened at home, right? We're sitting here playing with corn syrup for the last make this thing happen. And here's the green. It's right there. I'll try to keep it out that way. All right. So 3 different colors. So you can see where they are, 1, 2, and 3. All right. If I take the crank now, I'm going to crank, and you can actually see the colors start to mix. Okay. So put your hands right here.
Yes.
So it doesn't move.
Crank it up, Steve.
Ready? So here we go. Let's start to crank the colors. There's 1 turn, and you can kind of see the color mixing there. There's 2. There's 3.
Oh, wow. Yes.
And finally, there's 4. Let's give it 1 more for good measure. And there's 5.
Okay.
Got it?
Yeah.
All right. So take a look at this. It is mixed up.
Okay.
If the camera looks at this, you can see that we have complete color mixing down inside. If, however, it's kind of like a deck of cards laying a deck of cards out. If you take the deck of cards and scoop them back up again, exactly the way that you did before, in physics we call it laminar flow, kind of like that. You can maybe go backwards. Ready? Watch this. To show that we're not doing this tape backwards. Watch this. I'm actually going to spin backwards. We have to do 5 spins. There's 1. Here's 2. It's going to come around to 3. Here's 4. And we are lucky. Would you take a look at this there? Here's number 5. We are back in time.
Wow.
Isn't that really, really pretty? So all
That's
3
live.
of
That's
these-
real.
That's the real thing. Isn't that beautiful? Now, I don't even try to profess that I understand that the Reynolds law, the Reynolds number is under 1, and this is laminar flow. But we're going to put it up on the website. We're going to share it with a whole bunch of people. Some great people at the University of New Mexico. He's the first person I saw actually do this, Kevin Cahill. And so we recreated it this way, and we kind of wanted to show it to you. I think it's just an amazing thing to talk about chaos and order. Right. And I appreciate you
Clean it all up. Okay, that was
Put it up on the
fun. My
website.
first Steve Spangler.
And you didn't even look. No words or anything.
Yeah,
You're
I know.
fine.
So I think it's a very interesting test. I don't know if you had seen this before. So there are even better versions of this test on YouTube. If you look at search for this test on YouTube, if you search for laminar flow, you get videos similar to this. And there was even a better test where you go back, you reverse the flow, you get the final point you get is much closer to the initial point. In this test, it wasn't that good. I mean, the final.
It's a little wall that you see that's
So the dots at the beginning are,
you can see what happened.
distinct and has, nicely shaped. But when you go back in time, they're a little bit mixed up. But still.
Clean it up. You didn't even look. No burns or anything.
So here you don't get those distinct dots anymore. But again, I think it's really very impressive. Don't you think so? Okay, and in fact, we see this effect in our daily lives. So I don't know if you ever wondered this, but you know these toothpaste with stripes? When you squeeze the toothpaste, the toothpaste comes out in stripes, like some colorful stripes. And I was wondering that as a kid, how do they do that? And the way they do that is actually based on this principle. They have the conditions on the toothpaste is such that it corresponds to a perfect laminar flow. So that's how they fill that toothpaste into the tube. And they, just like in this case, when you squeeze the tube, the toothpaste coming out of the tube has this uniform stripes. The stripes don't get mixed up within the tube. And just like anything else, I have a video for that too. Let me. So there's just music here. I'm just going to turn it down. So this is what I'm talking about. It's always uniform, right? The stripes don't get mixed up. So you squeeze it and you always get these nice parallel stripes coming out of the tube. So there are three colors here: white, green, and blue. So as you see, there is nothing magic inside the toothpaste. It's just that when putting the toothpaste into the tube, they put in a certain order, first green, then white, and then blue. And then when coming out, it comes in the same order. It doesn't get mixed up within the tube. It doesn't matter, no matter how hard you shake it or how hard you squeeze it, it doesn't get disturbed at all. When you squeeze it, you get the stripes coming out in the same order they were put in the tube in the first place. I have this other video explaining Reynolds number, and I will post it to you and let you watch it on your own. And you can find very nice videos on YouTube if you search for it. The important thing here is all of this, the difference between laminar versus turbulent flow is determined by one parameter, and that's the Reynolds number. So it covers the effect of everything. It includes the effect of the speed of the flow, the viscosity of the fluid. Everything is included in one parameter, and if you know the Reynolds number, then you know what type of flow you will get. Let's see. So before we go, let me show you. Let's go through this example. Okay, so let's take a look at these two cases with some numbers. So here what I'm going to do is I'm going to show these two cases by using some numbers. Okay, so in one case I assume that there's water, and the other one there's honey. And here are some numbers. This is the density of water, and density of honey is pretty close to it. But their viscosities are quite different. The dynamic viscosity number for water is this much, 10 to the power minus 3. But for honey, it's much larger. It's 10,000 times greater. So let's put all these numbers into this Reynolds number formula. So in the first case, let's assume that a ball of diameter 1 centimeter is dropped into honey and water at a speed of 10 meters per second. So this is the speed of this object. Okay, the object hits the surface here, and I'm assuming that the speed at the contact instant is 10 meters per second in both cases. And I calculate the Reynolds numbers. So for the water, if you use the water viscosity here, you get 100,000, which is a quite large number. So typically, if it's greater than the critical value, you get turbulence. If it's less than that, you have laminar. So if you, for this example, the typical value is about 4,000. So it's much greater than that. So you expect a turbulent flow. But if you use the viscosity of honey, you get the Reynolds number is 15. So obviously this is less than the critical value and you get laminar flow. Okay? But now let's change some of the parameters. Now suppose that I have water, but now I am dropping a much smaller particle. Okay, so instead of dropping a ball with 1 centimeter diameter, let's assume that I'm dropping an object which is much smaller. Let's say a dust particle with a diameter of 10 to the power minus 5 meters is dropped into water. At a lower speed, the speed is 1 meters per second as opposed to 10 meters per second. And you see that even if I use the water viscosity here, the Reynolds number for this hypothetical example turns out to be 10. Okay, so that means if I take a very tiny particle on a microscopic level, only 10 microns, and if I drop a 10 micron particle into water, it will behave like this. Even though it's water here, just because the particle is very small, it will sink slowly into water without causing any turbulent reaction. Or let's see. You have the similar effect, the other example using honey. And in that case, assume that we have a ball of diameter 1 meter. So we have this huge ball. And it is dropped into honey at a much higher speed. So a 1 meter diameter ball hits honey, hits a pool of honey with a speed of 100 meters per second. If you calculate the Reynolds number for that, it turns out to be 15,000. So that means if you take a huge pool of honey and drop a 1 meter diameter object at 100 meters per second, you will get such a response from honey. You will see that the huge pool of honey would be splashing around and showing this turbulent reaction. So if you remember my previous question at the beginning of the lecture, so at first when you look at this, you get the feeling that this should be a much more viscous fluid than this. But to be able to tell the entire, to be sure, obviously, you need to know the other parameters, including the speed and the diameter, right? Because those are just as important as the viscosity. And the entire everything, the answer is really in the Reynolds number. Okay? Any questions? So hopefully you will remember what Reynolds number is in the future. And and as you see in this example, the effect of Reynolds number can be quite significant. So without checking the Reynolds number, you cannot really use any wind tunnel data for any real purposes. So whenever you obtain or you find a wind tunnel data, always they mention the Reynolds number, because without it, it doesn't really mean anything. So whenever you perform a test, the first thing you say is, okay, so I'm testing this model in this Reynolds number, and these are the results. And only then that data will become meaningful. So for sometimes it is hard to match the Reynolds number. So you have a huge aircraft flying at a very high speed. It has a huge Reynolds number, and you can't really reach those levels in a wind tunnel. And sometimes some tricks are done. For example, instead of air, some other fluids are used in the wind tunnel, so that by changing the viscosity, you can match the Reynolds number closely. This is more useful, especially for low Reynolds numbers. So, for example, if you want to study the insect motion, like the flapping wing of a bird, the Reynolds number is quite low, right? For birds, it's under the 100 or so. And if you want to study that in a wind tunnel, you can't go to that low Reynolds numbers. So instead, they study flapping motion in water tunnel. They do the experiments in water because it's easier to match the Reynolds numbers in a water tunnel. Okay, so the viscosity in a flow is can be very important, and the effect of viscosity is measured using the Reynolds number. And whenever you do the experiments, you calculate the Reynolds number, and then that will give you the results for the real aircraft if the Reynolds numbers are close. Okay, let's see. I think this is all I really wanted to say for today. Do you have any questions? So I will be posting the videos of this lecture and the additional videos I showed in class on Meteo Online. And also I will be posting the past exam questions on Meteo Online as well. And now the exam date is final. It will be on March 22nd at 10 a.m. in the morning. So we have less than 2 weeks now. Okay, so I will see you on Friday.